Welcome to Unit 8, Lines and Planes, Lesson 3, Properties of Planes. So let's pause a moment and think about the term normal and as it applies to mathematics. So recall a normal is a line that is perpendicular to any curve, plane or surface. In calculus, a normal is a line that's perpendicular to the tangent. In physics, a normal is a force perpendicular to a surface. All right, so let's continue on. Given the scalar form of a line ax plus by plus c, the position vector to the line is ab. Are there any other vectors that are normal to the line? Well, absolutely there are. What are they? Well, basically, any scalar of a b, like k a b, where k belongs to the reals. All right, so here a line is illustrated below in 2 space. Draw at least 4 other, I think I might just do 3, that are normal to it. Compare their direction. Does this illustration contradict your answer in part A? Explain. So here's one, here's another, here's another. I'm only going to do 3. And of course, these are all perpendicular to the line. The direction of all of these are the same or opposite. In 2 space, all lines normal to another line are parallel. All right. Well, given the scalar ax plus by plus c, the position vector, again, we talked about this already, is ab. Now visualize 3 space. Visualize at least 4 lines that are normal to it. Compare their directions. Does the answer compare to part A? So this is a little bit hard because I'm going to draw lines in 3 space on a piece of paper or 2 space. Let's look. So here's one, here's another, here's another. Oops, where are you? There you are. All right. Hopefully you can see here. Well, again, these are all perpendicular. Hopefully you can see here that these are different because the directions are not all the same. In 3 space, many lines can be orthogonal to one line, but are not parallel to each. Non-parallel lines in 3 space are called skew lines. We'll learn more about this, I think, in lesson 5 or lesson 4. So what is so great about the normal vector? Consider a plane instead of a line. All right, so plane instead of a line. So here we go. The normal vector of the plane in 3 space. Given the scalar equation ax plus by plus cz plus d equals 0, the position vector normal to the plane is, well, ABC. Mr. Willis, that's easy, but who cares? Well, actually, this is quite important. Why? All right. Consider there are infinitely many vectors that are parallel to the plane. All right, here are some. Right here, here's one, here's another one, here's another one. I got one more in here somewhere. I think I do. No, maybe not. There it is. All right. So these vectors here are all parallel to this plane. Poorly drawn plane, I apologize. But again, I'm trying to draw a plane in 2 space. It's very difficult. All right. But all the vectors that are perpendicular to the plane are the same. What do you mean, Mr. Willis? Well, here. That vector right there is perpendicular to the plane. What does that mean? That means that this meets the plane at a 90-degree angle. I've also got another one here. Where are you, sir? Right here. Nice orange one. So I know that that guy is also perpendicular to the plane. But if you can look here, you can see that if I drew another one, I'm not going to draw one, but you can see that as many as I want to draw, they are all the same direction. Wow. Parallel, there are many, and they're not the same direction. Perpendicular, there's really only one, right? I could shift this orange vector over here. It would be the same as that blue vector. Okay, why is that important? So no longer, we don't need a point and 2 direction vectors. to define a plane. A plane can be defined by, and this is so important, can be defined with one point and the, here we go, normal vector, boom. Not a big enough boom. All right, kaboom. That is so important, and this is where things, we start making our life really interesting and easier, actually. All right, what does this mean? Write a scalar equation of a plane given a point and normal vector. So consider this. I've got the normal to the plane, 371, and contains a point. Write the scalar equation of the plane. Well, guess what? This guy right here, that is my A, B, and C. So I really have this. 3x plus 7y plus z plus d is equal to 0. The only thing I'm missing here is, of course, this guy here. Well, how do I solve for that guy there? Well, I'm going to use this as my x, y, and z, sub it in, and solve for d. So I'm going to have 3 times 3 plus 7 times negative 6, plus 4 plus d equal to 0. If I do this quickly, 9 minus 42 plus 4 plus d equals 0. So here, if I solve this quickly, I get d is equal to 29. So what is the scalar equation? My scalar equation is 3x plus 7y plus z plus 29 is equal to 0. Awesome. All right, not bad. Let's continue. Consider the plane that is normal of 371 and contains a point 3, negative 6, and 4. All right, that's the exact same thing we just did. Is the vector A parallel to the plane? Well, the vector A is parallel to the plane if and is perpendicular to the plane, then A dot n is equal to 0. What does that mean? Right? If this is parallel, the normal is perpendicular, that means that they must have a dot product of 0. Dot product should be equal 0. All right, so here we go. I am going to do A, so 2, negative 1, 1, dotted with the normal, 3, 7, 1. So this is equal to 6 minus 7 plus 1 equals 0. So what does that mean? A is parallel to the plane because the vector dotted with a normal is 0. All right, what else? Is vector B normal to the plane? If A and B are both normal, then they must be scalar multiples. So what does that mean here? I am simply going to write them, the normal and the B vector, I'm going to write them as ratios. So here I've got 3, that's for my normal, over negative 6. The first coordinates is equal to 7 over negative 14 is equal to 1 over negative 2. If I simplify this, I get negative 1 over 2 is equal to negative 1 over 2, which is equal to negative 1 over 2, and voila, this is all true. So it is. So that means that B is normal. All right, find another vector that's normal to the plane. So what I can just do is take my normal and do any scalar by it. So k times the normal. So here I will do, let's do 2 times the normal, which is 3, 7, 1. That would be the vector 6, 14, and 2. So that is another vector that is normal to the plane. Done. All right, continuing on. Here we go. Find a vector equation of the plane containing the points A, B, and C. All right, this is probably one of my favorite questions, and this is where the math gets really good. In order to write the scalar equation, we need a point. Well, I've got 3 of them, Mr. Wells. All right, that's great. And the normal vector. The normal vector is perpendicular to the plane. If we can get 2 direction vectors, A and B, The normal will be orthogonal to both. We will take the, how do I get a normal from two direction vectors? Going back to last unit, here we go. This is it. This is another boom moment, the cross product. So here I want to do A cross B. So step one, what do I need to do here? I need to find two vectors. So let's two direction vectors on the plane. So I'm going to find AB is equal to 3 minus negative 2 is 5, 1 minus 3 is negative 2, and 4 minus negative 1 is 5. So there's AB. Let's find another one. Let's do BC. So I'm going to do 2 minus 3, negative 1. 3 minus 2 minus, 3 minus 1 is 2. And then finally, negative 2 minus 4 is negative 6. Let's just confirm that. Yeah, we're good. All right, and you can see they're not scalars of each other. 5 over negative 1 is definitely not equal to negative 2 over 2, so we're good. All right, so I've got two direction vectors parallel to the plane. That is step one. Step two, we are going to take the cross product of the two direction vectors. Cross product of 1. This will give me the normal. So here we go. Alright, it doesn't matter which ones. I'm going to do 5, negative 2, 5, 5, negative 2, 5, and then I'm going to write negative 1, 2, negative 6, negative 1, 2, negative 6. Alright, let's go. So first coordinate will be 12 minus 5. Or sorry, 12 minus 10. So the normal will be 12 minus 10. The next one, let's do it in blue. So it's going to be negative 5 plus 30. And then the last one, we'll do it purple. So here I'm going to have 10 minus 2. And so my normal will be 2, 25, and 8. So I got my normal. What else do I need? I need a point. So I've got my, and again, this is going to be my, simply my A, B, C. All right, so I got my A, B, C. So step 3, we want to solve for my constant D. So I've got here 2x plus 25y plus 8z plus d is equal to 0. Let's sub in. Which point should we use? We'll use point, well, let's do b because I like that. It's pi. So we're going to sub in, it's all positive too, b, which is 3, 1, 4. So I'm going to have here 2 times 3 plus 25 times 1 plus 8 times 4 plus d is equal to 0. If I solve this quickly, I'm going to get d is equal to and d is equal to negative 63. So what do I have here? I have my equation. So my equation will be, so the scalar form will be 2x plus 25y plus 8z minus 63 is equal to 0. Step 1, find two direction vectors. Step 2, cross product, find the normal, which is your a, b, and c value. And step 3, solve for d. All right, beautiful question. Let's continue. Use properties of plane to write the equation. All right, I like this question a lot. determine the scalar equation. So parallel to the xy plane. So what do I have here? I've got three planes. I got this guy, and I've got this guy, x, y, and z. So parallel to the xy plane. So it's really this guy here. That is the xy plane. Very nice, Mr. Wills. So what does that mean? That means that is a normal. My normal must be basically just a vector on the z-axis. So my normal can be anything with a vector on the z-axis. So I'm going to go with easiest one, 0, 0, 1. There we go. So I've got my equation. So that means I've got z plus d is equal to 0. Plug in my point. Well, the only point I have here is my z, so it's going to be 6. 6 plus d is equal to 0. D is equal to negative 6. So my equation will be z minus 6 equals 0. And that vector there is parallel to the plane, xy plane. All right, contains the line perpendicular to this. So if it's perpendicular, key, that means the direction vector is actually my normal. And contains a line, that guy will here, this will be a point on a plane. So, again, perpendicular, got my normal. So my normal is 2, 1, negative 4. So now I really got 2x plus y minus 4z plus d equal to 0. Plug in my point. My point is 1, 2. So I'm going to have 2 plus 2 minus 16, that's negative 12, so d is equal to 12. So my equation will be, scalar equation on my line will be 2x plus y minus 4z plus 12 is equal to 0. All right. Next one, here we go. So this is like the homework question, question 5 from page 459. Consider the plane, the scalar equation of the plane, x plus 3y minus 5z plus 2. Determine the normal to the plane. Well, that's just my a, b, and c value. So this is just going to be 1, 3, negative 5. It says here, determine the coordinates of two other points, s and t on the plane. All right, well, I'm going to go, I'm going to go easy here, I believe. Let's see, I'm going to do y, z equal to 0, and I'm going to solve for x. So I'm going to find the x-intercept. So I have x plus 2 is equal to 0. So x is equal to negative 2. So point on the plane will be negative 2, 0, 0. And we'll call this my point. S, not a 5, but an S. All right, there's one. Let's do another one. Here we go. I believe I'm going to cheat a little bit here, but I believe if I have 2, 2, it's going to give me 8, 10. Yeah, so I'm going to use x is equal to 2, y is equal to 2, and I'm going to solve for z. A little bit of cheating. So I have 2 plus 3 times 2 minus 5z plus 2 is equal to 0. That's going to give me 2 plus 6 plus 2 is 10. Bring it over, negative 10. So I've got here z is equal to 2. So that means my other point will be 2, 2, 2. And we'll call that my point. Where are we here? I think I'm going to call that my point T. All right. So negative 2, 0, 0, 2, 2, 2. There we go. There are my 2 points on my plane. All right. So let's go to the next question. So let's try to remember that. So determine ST again. S is negative 2, 0, 0. And TP, T, which is back here, is 2, 2, 2. So 2, 2, 2. So here we go. ST must be 2 minus negative 2 is 4. 2 and 2. So this right here, this is a direction vector on my plane. So direction vector on plane. Oops, direction vector. Come on, Mr. Wills. All right, there we go. Direction vector on plane. So now it should show that ST, because it's a direction vector on plane, it's parallel to my plane. It's perpendicular to the end. So I want to show that ST dotted with N is equal to 0. So here we go. I'm going to have 4, 2, 2, dotted with 1, 3, negative 5. So here I'm going to get 4 plus 6 minus 10, and here we go, is equal to 0. Therefore, ST is orthogonal to the normal, which is awesome, which makes sense. All right, last question. Here we go. Just like question 18 on page 459, consider the planes 1 and plane 2. Determine K if plane 1 and plane 2 are parallel. If the planes are parallel, their normals must be, their normals must be parallel. So what do we do here? I'm going to write them as, I'm going to do normal 1 is 2, 6, and negative 2, and then normal 2 is 5, 15, and K. I'm going to write them again as ratios, like so. Alright, so I want to solve for K here. I can see that 2 or 5. If I multiply by 3, it is true. So what I'm going to do now is I'm going to focus on these two, cross multiply and solve for K. So I'm going to have 6K is equal to negative 30. So K is equal to negative 5. And there we go. Alright, last one, determine K if plane 1 is perpendicular to plane 2. If the planes are perpendicular, the normals must be perpendicular or orthogonal. If that is so, their dot product must be equal to 0. Alright, determine K, so here we go. I am going to dot the two normals together, so I'm going to dot plane 1, normal of plane 1, sorry, let's fix that. So I'm going to dot the normal of plane 1, dotted with normal of plane 2, and set this equal to 0. So I'm going to have 2 times 5 plus 6 times 15 plus negative 2 times K is equal to 0. I do a little bit of fast math here, 10. That right there is, I believe, 90, so we're at 100. So we have negative 2K is equal to negative 100. So that means K is equal to 50. Sorry, that's a K right there. That's a 2 there. All right, so that means that if K is equal to 50, then the planes are perpendicular. All right, that is the end of lesson 3.